To understand how to reduce the risk of developing cancer, we first need to look at the environment in which cancer begins. While I am an artificial intelligence and do not physically look through a microscope, I can share the perspective of a pathologist in oncology. When pathologists examine tissue samples, they're not just looking for cancer cells, they're looking at the neighborhood surrounding those cells. We call this the tumor microenvironment. One of the most consistent features found in these cellular neighborhoods, long before a tumor even forms, is inflammation. To give you a comprehensive overview of how to protect your cellular health, we will explore the profound connection between chronic inflammation and cancer, followed by actionable, daily strategies to cool down this inflammation and reduce your risk. This explanation is designed to be easily listened to, breaking down complex biological processes into clear, everyday language. Part 1. The hidden link between inflammation and cancer. Inflammation is not inherently bad. In fact, it is a vital, life-saving immune response. When you cut your finger or catch a virus, your immune system dispatches white blood cells, defensive chemicals, and increased blood flow to the site of the injury or infection. This is known as acute inflammation. It is characterized by redness, heat, swelling, and pain. Once the threat is neutralized and the tissue is healed, the acute inflammatory response shuts off, and your body returns to a state of balance or homeostasis. The danger arises when this process fails to shut off. This is called chronic inflammation. Imagine acute inflammation as a controlled fire used to clear away debris. Chronic inflammation, on the other hand, is like a smoldering underground coal fire. It is quiet, persistent, and slowly damages the surrounding landscape over years or even decades. You might not feel it, but your cells certainly do. How chronic inflammation drives cancer. From a pathology standpoint, chronic inflammation creates a perfect storm for cancer development through three main mechanisms. First, chronic inflammation damages your DNA. The white blood cells that are constantly active in a chronically inflamed area release highly reactive molecules called reactive oxygen species. These molecules are meant to destroy pathogens, but when they linger for years, they act like biochemical shrapnel. They strike healthy cells and damage their DNA. Over time, this cumulative DNA damage can cause a normal cell to mutate into a cancerous one. Second, inflammation promotes cell division. When tissue is constantly inflamed, the body is constantly trying to repair it. The immune system sends signals instructing nearby cells to divide and replace the damaged tissue. However, every time a cell divides, there is a small chance of a genetic copying error. When you force cells to divide rapidly and continuously in an environment full of DNA-damaging molecules, the risk of a cancerous mutation skyrockets. Third, inflammation helps tumors survive and grow. If a single cancerous cell does form, a chronically inflamed microenvironment acts like fertilizer. Inflammatory chemicals signal the body to build new blood vessels, a process called angiogenesis. This inadvertently provides a newly formed tumor with a dedicated blood supply, feeding it the oxygen and nutrients it needs to grow. Furthermore, inflammation can suppress the specific immune cells whose job it is to hunt down and destroy rogue cancer cells. We see this sequence of events in many well-known cancers. For example, chronic inflammation of the liver caused by hepatitis B or C dramatically increases the risk of liver cancer. Chronic inflammation of the colon, such as an inflammatory bowel disease, increases the risk of colorectal cancer. Chronic acid reflux, which inflames the lining of the esophagus, can eventually lead to esophageal cancer. Understanding this biological reality is empowering. If chronic inflammation is the fertilizer for cancer, then reducing inflammation is how we starve it. Part 2. The mechanics of speed, how eating fast drives cellular fire. When discussing nutrition and cancer prevention, conversations typically center on what is on the plate: carbohydrates, fats, fiber, and vitamins. However, from a cellular kinetic standpoint, how fast you consume those nutrients fundamentally changes your body's metabolic and inflammatory response. The speed at which you eat directly dictates the rate of rise of glucose in your bloodstream. This distinction between total sugar consumed and the velocity at which it enters your blood is critical to controlling systemic inflammation. The physics of the digestive funnel. Picture your stomach as a dynamic holding tank and mixing valve. When you eat rapidly, you chew less, sending large, coarsely broken pieces of food into the digestive tract. The stomach is forced to process this incoming load quickly, dumping its contents rapidly into the small intestine, a process known as rapid gastric emptying. The lining of the small intestine immediately absorbs these rapidly released simple sugars into the bloodstream. Conversely, when you eat slowly, thorough chewing mixes food thoroughly with salivary enzymes like amylase, initiating digestion in the mouth. Slow eating allows satiety and gut hormones, such as GLP-1, glucagon-like peptide, 1, and CCK, cholecystokinin, time to release. These hormones signal the stomach to slow down gastric emptying, releasing glucose into the small intestine in a controlled trickle rather than an overwhelming surge. The velocity problem, glycemic slope versus total volume. Think of your bloodstream like a highway. If 100 cars enter a highway over the span of an hour, traffic flows smoothly. If those same 100 cars merge onto the highway in 45 seconds, you create an immediate catastrophic bottleneck. In metabolic biochemistry, we evaluate this as the difference between overall glycemic load and glycemic velocity. Glycemic velocity equals the change in blood glucose divided by time. When you eat rapidly, your blood sugar doesn't just rise. Its slope becomes extremely steep. That sharp rate of increase triggers a cascade of inflammatory signals at the cellular level. The inflammatory cascade of a sugar surge. A sudden spike in blood sugar initiates three distinct, pathologically significant responses. 1. Pancreatic overdrive and hyperinsulinemia. Your pancreas responds not only to the absolute presence of glucose, but to the speed at which glucose levels are rising. A sharp surge forces the pancreas into an emergency response, flooding the bloodstream with insulin to clear the sugar before it damages vascular linings. Insulin acts as a powerful signaling hormone for tissue growth. Chronic surges in insulin elevate levels of IGF-1, insulin-like growth factor 1. IGF-1 acts like an accelerator pedal for cellular proliferation. If a cell in your body has already sustained a minor DNA mutation, high circulating levels of IGF-1 signal that damaged cell to divide and multiply rather than undergo natural cellular self-destruction, apoptosis. 2. Mitochondrial overload and ROS production. Your cell's powerhouses, the mitochondria, convert glucose into usable cellular energy, ADP. When a rapid wave of sugar floods the cell all at once, the mitochondrial processing machinery becomes overwhelmed. This excess influx causes electrons to leak from the mitochondrial electron transport chain. These free electrons react with surrounding oxygen to form high concentrations of reactive oxygen species, ROS. As established, these ROS strike nuclear DNA, causing strand breaks and oxidative damage. 3. Activation of NF$/B, the master inflammatory switch. Surging intracellular glucose directly triggers an internal protein complex known as NF$/B, nuclear factor kappa B. NF$/B operates as a master genetic switch for inflammation. Once activated by a rapid sugar spike, it enters the cell nucleus and instructs the cell to produce pro-inflammatory signaling proteins, specifically interleukin-6, IL-6, and tumor necrosis factor alpha, TNF$/alpha. These circulating proteins keep systemic tissue in a persistent state of low-grade chemical inflammation. Part 3. Practical strategies to eat slower and cool the fire. Slowing down your eating pace acts as a primary physical buffer against metabolic surges. By combining mindful eating mechanics with an anti-inflammatory diet, you actively lower your baseline cancer risk. 1. Master the mechanics of slow eating. Chew thoroughly. Aim for 15 to 20 chews per bite. Mechanically reducing food to a liquid state maximizes salivary enzyme mixing and gives gut hormones adequate time to signal your brain and slow down gastric emptying. Sequence your meal strategically. Eat your meal in a specific physical order. Fiber and vegetables first. Fiber creates a physical mesh in the intestinal tract that slows down glucose absorption. Proteins and healthy fats second. These nutrients further delay stomach emptying. Carbohydrates last. Consuming carbohydrates after fiber and protein significantly flattens the resulting glycemic curve. Pace your bites. Set your utensils down on the table between bites. Introducing a 10 to 15-second pause between morsels turns a rushed 5-minute meal into a restful 20-minute event, allowing satiety signals to register before overconsumption occurs. 2. Choose anti-inflammatory foods. Beyond pacing, the quality of your food dictates your cellular health. Incorporate omega-3 fatty acids, found in wild fish like salmon, sardines, and mackerel, as well as walnuts and flax seeds. Omega-3s serve as molecular precursors to anti-inflammatory signaling molecules called resolvins. Prioritize plant diversity and antioxidants. Brightly colored vegetables, berries, dark leafy greens, and cruciferous vegetables contain rich concentrations of polyphenol and phytonutrients that directly neutralize free radicals. Utilize anti-inflammatory spices. Turmeric containing curcumin, ginger, garlic, and rosemary contain bioactive compounds shown to inhibit the inflammatory NF$/kappa-B pathway. Increased dietary fiber. Soluble and insoluble fibers feed the gut microbiome. Beneficial gut bacteria ferment fiber into short-chain fatty acids, such as butyrate, which cool inflammation throughout the colon lining. Minimize pro-inflammatory triggers. Reduce intake of ultra-processed foods, refined sugars, trans fats, and processed meats containing synthetic nitrates. Part 4. Comprehensive lifestyle interventions. Slowing your eating pace fits into a broader daily lifestyle routine designed to quiet systemic immune overactivity. Physical activity. Muscle as an anti-inflammatory organ. When muscles contract during physical activity, they act as endocrine structures, releasing specialized peptides called myokines into the blood. Myokines specifically counteract systemic inflammatory signaling. Furthermore, regular exercise reduces visceral fat, the deep abdominal fat surrounding internal organs. Visceral fat is not dormant. It continuously secretes inflammatory cytokines into circulation. Aim for at least 150 minutes of moderate activity, such as brisk walking, swimming, or cycling, along with 2 strength training sessions each week. Sleep, the cellular repair window. Deep sleep is the body's primary period for structural repair. During non-REM sleep, systemic inflammation dials down, and the body produces enzymes dedicated to repairing damaged DNA. During dark hours, the pineal gland produces melatonin. Beyond regulating sleep cycles, melatonin is a highly potent antioxidant that scavenges ROS within cell nuclei. Prioritize 7 to 9 hours of quality sleep nightly, keeping the bedroom dark and free of blue light screens prior to bed to preserve natural melatonin production. Stress reduction. Regulating the nervous system. When you experience chronic stress, your adrenal glands continuously secrete cortisol and adrenaline. Over time, immune cells lose sensitivity to cortisol's regulatory cues, leading to unchecked inflammatory output. Interestingly, eating quickly is often a direct physical symptom of living in a sympathetic fight or flight state. Consciously choosing to sit, pause, and eat slowly forces your nervous system to engage the parasympathetic, rest and digest branch. Practices like deep diaphragmatic breathing, meditation, or quiet time outdoors reduce baseline cortisol and help regulate immune cell activity. Minimizing environmental exposures. Avoid direct drivers of tissue damage. Tobacco smoke exposes tissues to thousands of carcinogenic compounds, inducing intense, chronic inflammation in pulmonary tissue. Alcohol metabolizes into acetaldehyde, a chemical that directly damages DNA strands and impairs enzyme repair mechanisms. Reducing or eliminating these exposures removes major external sources of cellular stress. Conclusion: when viewed through the lens of oncology and pathology, cancer is rarely an instantaneous event. It is more often the culmination of long-term cellular strain, driven by a persistent environment of chronic inflammation. While we cannot rewrite our underlying genetic code, we retain significant influence over our metabolic microenvironment. By consciously slowing down our pace of eating, we prevent rapid glycemic spikes, reduce insulin surges, and protect our cell structures from oxidative stress. Combined with nutrient-dense foods, consistent movement, restful sleep, and stress management, eating slowly becomes a powerful daily habit for maintaining long-term cellular health. Thank you for listening. Please click like, subscribe, and share our channel to your beloved ones.